this talk is towards the theoretical end of the spectrum. My goal is to survey some recent work in the algorithms community relevant to processing large graphs. The focus is on a particularly useful and kind of fundamental technique called sketching that allows you to reduce communication when you have data that's distributed across numerous machines, and also allows you to come up with efficient kind of stream processing algorithms for graph data. So I'm going to be a little slack with attribution of who came up with which idea. But fortunately, I've got an excuse for this, and that excuse is that there's a corresponding survey that I put together. It's in Signaled Records, or it's on my webpage, so if you just search for my name, and you'll find the survey that goes into more depth about almost everything I'm going to say today and tells you who came up with what. Okay, so there's two main so I guess distributed data was pretty clear. It was just like when you've got data distributed across different machines. I'm going to need to tell you a little bit more about exactly what sketching is, and you probably already have a rough idea what I mean by streaming, but I'll be a bit more concrete with what I mean by streaming graph data in a second. But first of all, I want to give you a very kind of simple, clean communication problem, communication complexity problem, that's going to play a fairly large role in this talk. So I'm hoping kind of everybody gets the talk, gets this problem. So the problem is as follows. Suppose you have n people, okay? N people in a room. Suppose it's you guys. And let's suppose everybody here has an address book that lists their friends amongst the people in the room. Okay, we'll assume that friendship is always reciprocated. So therefore, there's an underlying social network that's undirected of the people in this room. Okay? But each of these individual people only knows their immediate friends. Okay? So you know who your friends are, but you don't know which of your friends are friends of each other, et cetera, et cetera. Okay? The question I want to pose, or the kind of situation I want to think about, is suppose the following. Suppose that simultaneously these n people need to look at their data, their address book, compress it down to a small message, a small number of bits, and communicate it to a central player. Okay, so everyone in the room looks at their address book. Since they could be friends with potentially anybody else in the room, and let's suppose there's billions of people in the room, their address book is a very big document, but they're trying to compress it down to something very small that you could write on a postcard. You send those postcards to the central player. The central player must then be able to look at the postcards and deduce whether the graph is connected. Okay? So is the setting and the goal clear? Okay, fantastic. Okay, so the question is, how long do these messages need to be? How many bits need to be contained in these messages? So bear in mind, as I said, every address book, you can think of it as a characteristic vector of length n. So every player starts off with n bits of information. If every player sends those n bits of information to the central player has all the information, can do whatever he likes. How much information does he need to get from each player to test whether the graph is connected? Well, the first results I'm going to show in this talk, and I think it's fairly surprising, is it's sufficient for each of these players to send polylog n bits of information about their address book to the central player. And I want to clarify that these n players don't get to communicate amongst themselves. They just look at their own address book, compress it down to a small message, send it to the central player. Okay. So I claim this is surprising, and you'd be forgiven for not believing it, this theorem. Okay? Let me say why you should be dubious about this theorem. What about a graph that has a bridge? So let's say there's one player here. Maybe he's connected to a whole bunch of people over there. There's another player, Eduardo, here, that's connected to a whole bunch of players over there. But there's a single edge that links, I guess, Cameron and Eduardo here that is essential to graph connectivity. If that edge is there, the graph is connected. If that edge is not there, the graph is not connected. So the connectivity property is very sensitive to this one edge. Well, in a graph like this, it would seem that one of these two players needs to send an awful lot of information about their address book. Why is that? Well, the central player needs to know about whether this bridge exists in this graph, whether that special friendship was there or not, because that determines whether the graph is connected or not. But unfortunately, neither of these two players know that that edge is any more special than their other friendships. Okay? And they could easily have omega n other friendships. So the two players in question, they've got n friends. One of them might be special. They don't know which one. If they're going to guarantee that the central player finds out about that special edge, it seems that one of those two players needs to send omega n information. It needs to send at least a constant amount of information about each of their friendships. Okay? So I said it seems, it appears, like, you could try and turn this into a formal lower bound, but that's not going to work. The reason it's not going to work is because I'm going to present you an algorithm that shows that despite this kind of bad example, it's possible for every player, including these two players, to compress their address book down to just polylog n bits, and everybody will be happy. One clarification I want to make is a lot of my pictures, the way I describe things, I'll describe things in terms of social networks, but I'm not going to assume any properties of the underlying graph. Like, all these protocols and algorithms I'm going to present will work for arbitrary graphs. If nothing else, I hope you find that theorem a little surprising and are motivated to keep paying attention for another 10, 15 minutes until I tell you how it's done. Then you can go back to sleep. Okay, so that's the motivating problem I want to think about for a while. I should tell you, I promised to tell you a little bit about streaming and sketching, so let's do that. So the streaming model in terms of graphs is just the following. So the input is a long stream of data describing the graph. In particular, this stream consists of edges being inserted or deleted from the underlying graph. And the goal is you get to observe the stream, you get to monitor the stream, and at any given time, you want to be able to you want to be able to answer questions about various properties of the graph that the stream has described. So, for example, at any given time, maybe you're asked, like, well, how many connected components are on the graph so far? Again, this would be a trivial problem if you got to remember all the data that you'd seen in the stream so far. But in the data stream model, the catch is that you don't have all the stream, or you don't have enough memory to remember the entire stream. Rather, you have a limited amount of memory. This is sometimes polylogarithmic in the length of the stream. For graph streams, often the restriction that we focus on is, let's suppose you have roughly memory proportional to the number of nodes in the graph rather than the number of edges in the graph. So for a dense graph, you need to throw away some information. And you still need to be able to kind of return accurate answers about various questions you could be asked about the graph. So this is graph streaming. Has a lot of really nice prior work in the last 20 years on various other streaming problems that focused on estimating numerical statistics or solving geometric problems. In the last 5, 10 years, there's a now growing body of work designing streaming algorithms for more kind of structured data, in particular graph data. Looking at problems like estimating the distances between two nodes of a graph, estimating cuts, size of matchings, finding dense components. This list is by no means exhaustive, but again, I point you to the survey where you can find an attempt to be exhaustive of the work in this area. Okay, so that's streaming. Sketching is a name for a technique which I'm sure you've come across in your own field. The idea is, let's suppose you have a large amount of data, and you encode that as a big, long vector V. Okay? The idea behind linear sketching is essentially you take some sort of projection of this vector. Maybe it's random, maybe it's deterministic. Take a projection M of V to get this shorter, kind of lower dimensional vector MV. And the idea is that you design, okay, the projection you use is dependent on the problem you want to solve. Okay, so if you wanted to estimate, say, the L2 norm of this vector, you'd use one particular matrix here, M, and then you'd look at the projection MV, you'd post-process that projection, and you'd get a good estimate for what the L2 norm of this vector was. If you wanted a different problem saying, so let's try and estimate the support size of that vector, you'd use a different random matrix M. Okay. So that's linear sketching. As with streams, there are many kind of existing results for estimating numerical properties of vectors, or sometimes you can code geometric problems as a vector, and you can you can design a linear sketch, a random linear sketch, that will allow you to do something like estimate the diameter of a point set, or try and cluster some data. So sketching, as I said, kind of turns up under different names in many different communities. There's now an extensive theory of linear sketching, connections to kind of fingerprints and hashing. In compressed sensing, the idea is that you assume that this vector V is sparse, it only has a small number of non-zero elements, and from the projection, you can actually reconstruct V exactly. In all this other work, you're just trying to estimate properties of V. It's also a widely applicable technique because it's embarrassingly parallel, in the sense that if the data corresponding to vector V resides on one server, the data corresponding to vector U resides at a different server. If I want to kind of compute the linear sketch of U plus V, well, I can construct the linear sketch of U at one server, linear sketch of V at the other server, and just communicate the sketches. And this will be more communication efficient if the dimension of the projection is a lot less than the dimension of the original data. Okay. So as I said, most of this work, previous work has been done on estimating numerical statistics of this vector V. Question motivating much of the recent work is, well, can you use this like a random projection technique for the purposes of solving graph problems? Okay. And that's what I plan to show you. Okay, so now I've told you a bit of, so sketching is also related to, I said it was related to distributed data. It's also related to streaming data, the idea being that, let's say the stream is defining this vector incrementally. So every item in the stream maybe says that, well, the 10th element of the vector you should increment or you should decrement. Since the sketch is a linear projection, it's sufficient as you go through the stream just to be maintaining that projection. You don't need to actually kind of materialize the big, long vector. Like, all that happens is, at some point in the stream, when it says, increment the 10th element of the vector by 1, well, you can simply update the projection of that vector by just adding the 10th row of the matrix M to your projection. Okay, so that's streaming, sketching, and the connection between the two. Okay, so back to our initial problem. Okay. The main idea, the high level of how we're going to solve that connectivity problem is that each of the players, each of those N players, is going to send a linear projection of their address book. So it's going to project the length N vector that encodes their address book down to a shorter vector M times their address book, where M is some like random linear matrix. Okay? I should say M can't just be any random projection. It needs to have some specific properties, but we'll get to that in a second. Okay. Well then, what does the central player do? He's received a random projection of everybody's address book. Great. Okay, well the idea behind actually kind of proving results in this kind of communication setting is as follows. If we had all the data that described the graph, if we had all the original address books, we could pick our favorite algorithm from an algorithm's textbook for connectivity and run it on these N address books and get some answer. Hopefully it'll be a correct answer. The idea with sketches is, first of all, each of the address books are sketched, and so this is the data that's received by the central player. The template for the next three algorithms I'm going to show you is that the central player can run an algorithm that's somehow analogous or homomorphic to the original algorithm on the compressed data. Okay? And this compressed data, there's like kind of, I guess, n vectors of roughly length n here, so there's n squared bits of information. There's only roughly n bits of information here. So the central plate can run an algorithm on the compressed data and hopefully get the same answer. Okay, so this is fine as a high level, but I need to actually show you this idea works, at least for some problems. Okay, any questions? What I'm going to tell you will only work if we don't lose information about that bridge. Okay, so the first question was, don't we lose information? Yes, of course we lose information. Like, initially there's n squared bits here, we've compressed it down. Okay, so we're definitely throwing away a lot of information. The idea is to carefully design these random projections M such that with high probability we don't lose information we care about. In the case of connectivity, we don't lose the information about the bridge, for example. Okay. The other clarification based on questions I've been asked in the past is that all these random predictions M, those are chosen independent of the data. Like, you decide a protocol with a particular random matrix M, and then whatever input we end up having to deal with, whatever address books we have, this has got to work with high probability. Okay. So let's say this is the template for the algorithms I'm going to show you, in particular starting off with the connectivity. So I basically need to show you, to show the connectivity result, I need to show you two things. I need to tell you what the basic algorithm is that we'll try and emulate in sketch space. That's ingredient number one. And ingredient number two is I need to tell you exactly how this sketching works. Okay? So first part of the talk, let's deal with connectivity. And the result we're shooting for is that you can test connectivity with only a polylog n bit message from each player. I won't go into the details, but this result actually implies a data stream algorithm that uses n polylog n bits for processing dynamic graphs when there can be edge insertions and edge deletions. Okay, so two ingredients I need to show you: a basic algorithm we want to emulate in sketch space, and how we actually can do the mapping to sketch space. So the basic algorithm is incredibly basic. Yeah, I get no points for coming up with this algorithm. But here's a simple algorithm that we're going to emulate. So you start out with a massive graph, this graph from 5 nodes. And for each node, you pick an incident edge. So let's say the red edges are the edges you've ended up picking. Like this node, you pick this instant edge, that node, you pick that instant edge, maybe that node, you also pick that instant edge, etc. So after this step, if you look at the red nodes, you've got two connected components. This guy and this guy. Next step of the algorithm, for each connected component in that graph, pick an instant edge. Well, after you've got these two connected components, there's actually only one instant edge left, this guy here, so you pick him. Okay? At this point, if you just look at the red edges, you've collapsed everything down to a single connected component. If this was a bigger graph, we'd potentially need to keep on repeating this process until everything's collapsed down as far as it's going to collapse. It's not hard to argue that the number of rounds this algorithm can take is going to be at most log n. Basically because the size of connected components kind of doubles in every step, and there's only n nodes to start with. Okay, so that's a basic algorithm that I could run if I had all the address books. So the challenge now is like, come up with a way to sketch the address books such that I can run something that's equivalent to this algorithm on the sketch data. Okay. So the first thing I need to do is I need to tell you how to encode your address book as a vector, so we can start talking about linear projections of vectors. The way we're going to do this is as follows. So I'm giving you a formal definition there, but you don't need to read it. Let's kind of think of what we do for this specific graph on 5 nodes. So for each of these nodes, we're going to come up with a vector. So for node 1, we're going to come up with the vector A1. So the vector A1 is a length n choose 2 vector, and the entries of this vector correspond to all possible pairs of nodes in the graph. So we've got the pair 1, 2, 1, 3, 1, 4, 1, 5, all the way up to 4, 5. Okay, so A1 is a vector of length n choose 2. And the non-zero entries of A1 correspond to instant edges on node 1. So node 1 has instant edges 1, 2, 1, 3. And lo and behold, The entry for 1, 2 is 1, the entry for 1, 3 is 1, and the rest are all 0. Okay? Similarly for A2, for node 2, we can come up with this length n choose 2 vector A2, where the non-zero entries correspond to incident edges on node 2. So the incident edges on node 2 is just 1, 2, and 2, 3. Lo and behold, 1, 2, 2, 3, and the rest are all 0. The only little wrinkle is that the non-zero entries will either be 1 or -1. I'm going to adopt a convention that if you're friends with someone with a lower label than you, you're going to put a -1. If you're friends with someone with a higher label than you, you're going to put a 1. And the reason we do that is because it gives us this nice property. Maybe at some point, I'll be interested in the connected component consisting of nodes 1 and node 2. And I'll be interested, what are the edges that are incident to this connected component? So I'm looking for the edges 1, 3, and 2, 3. Well, look what happens when I add the vectors A1 and A2 together. Those +1s and -1s cancel in a nice way, such that if I take A1 and A2, add them together, the non-zero entries correspond exactly to 1, 3, and 2, 3, exactly the edges across this cut. Okay? And this is more general. Like if I defined A1, A2, A3, A4, A5 in this example, and if I take any subset of those nodes, add together the corresponding vectors, the non-zero entry of the resulting vector, basically the support is just all it means the non-zero entries of the sum of the appropriate vectors correspond exactly to the edges across the cut from S to the rest of the graph. Okay. So just a nice, neat little property that we're going to use. Okay, so this was the first step. So you've taken your address book, encoded it as a length n choose 2 vector. Now we're going to do a random projection on that length n choose 2 vector. And at the moment, I'm going to treat this random projection as a black box, but I'll come back and say a few words about it in a second. So there's a previous result by Johari et al. That says there's a way to design a random matrix M that projects down from length n vectors to log n vectors, such that, so we randomly pick a matrix according to a certain distribution, such that if you come along with any arbitrary vector A and tell me what the projection of M times A is, I, just by looking at that projection, can deduce one of the non-zero entries in the vector you started with, A. Okay? So if you're familiar with compressed sensing, I want to point out the difference from this and compressed sensing. If you're not familiar with compressed sensing, please tune out for the next 20 seconds. So in compressed sensing, the idea is that from your projection, you can deduce all the non-zero entries of A on the promise that A is sparse. For this result, there's no promise about the sparsity of A, but all you're guaranteed is to recover at least one entry of the vector A. Okay. So for the people who tuned out, please tune back in. Okay, so we're pretty much done for the sketch. All you're going to do is you're going to take your address book. Like if you're a player I, you're going to encode your address book as vector AI. You're then going to apply a random matrix M with these properties to that vector. Okay? You then send me, let's pretend I'm the central player, all those projected address books. And then I am going to try and run that initial algorithm we talked about based on not the original data, but based on those sketches you've sent me. Like you've each sent me kind of polar again bits. So how do I do this? Well, emulating the first round of the algorithm is easy. Remember, the first round of the algorithm was just for every node in the graph, pick an instant edge. Okay, I'm all set. Like, you know, say Mike, he sent me a vector AJ. Oh, sorry, rather he sent me a projection M times AJ. By the properties of the random matrix M, with high probability, from the projection Mike sent to me, I can work out what one of his incident edges, one of his friends, one step at a time. Sorry, from the projection Mike sends me, I can work out one of the non-zero entries of the vector aj that he turns his address book into. And then from the properties of aj, non-zero entries of aj correspond exactly to incident edges. So from the message Mike sends me, I can work out what one of his friends are. Okay. That's not too impressive. He could have just randomly told me one of his friends. But what's going to be important is that we can use these sketches to emulate subsequent steps of the algorithm. Okay? So the algorithm is going to keep on running for kind of log n rounds. And at various points in the algorithm later on, we're going to have these various connected components in the graph. And we're going to be asking, like, say, for the connected component S, give me an incident edge on that connected component S. Okay? How am I going to do this? Well, this is where the linearity of those random projections really comes into savors in a simultaneously trivial and, I maintain, surprising way. Okay, so to find an instant edge on component S, I just kind of look at the messages that were sent to me by the corresponding people. Kind of say it was players 1, 2, and 3. I will take the m times a1 plus, and m times a2 and m times a3 and add them all together. Okay? So I add together your messages. By linearity of the projection, this just corresponds to m, the projection, of the sum of your original vectors. By the properties of m, this allows me to deduce a non-zero entry in the sum of those original vectors. And by that little lemma I had in the previous slide, the non-zero entries of the sum of these vectors correspond exactly to edges across the cut from S to the rest of the graph. They correspond exactly to incident edges on the component S, which is all I need. Like, the fundamental operation of that original algorithm is at any point in time, I need for any given collection of nodes, I need to find an incident edge out of that component. This allows me to do that. If you've understood, if you followed everything I've said, then I'm very happy. There are a couple of things I've glossed over regarding kind of quite how we do the probabilistic analysis. Like, kind of the slight issue being that every m with high probability for an arbitrary vector A will return a non-zero element. But you need to make sure, like, you can apply the union bound in the right way to make sure that the entire process succeeds with high probability. It's a little bit more detailed than these things normally are, but I still maintain that the entire algorithm would be simple to teach in maybe even in an undergraduate algorithms class once you've taught randomization. How are we doing for time? Because really, if you get this, then I don't care what else you really get from the talk. So there was a question about, like, if this projection such that you'd be able to deduce one entry of the vector. And I don't want to leave that as a mysterious black box. I want to kind of tell you enough information for you to realize that that's not something particularly magical either. So, okay, so let me just talk about this kind of this random projection that allows you to work one non-zero entry of the vector. So this general technique is called L0 sampling. And that was the lemma that I was claiming had been previously proved. So when I say a random m, it's certainly not going to be like, kind of every entry of m is like kind of Gaussian, Cauchy, +1, -1, or anything like that. It's actually going to be quite a non-uniform random matrix. In particular, the matrix, like kind of, let's say this dimension is n. So the top row of the random projection matrix is going to be pretty much all ones. In the second row, roughly half of the entries are going to be 1, and the other half 0. In the next row, roughly a quarter of the entries are going to be 1. The next row, roughly an eighth of the entries are going to be 1, et cetera, et cetera. Okay. What this means is that when you come along with a vector A, no matter what it is, no matter how many non-zero entries it has, I claim there's going to be one entry of the projection that corresponds to a single entry of that vector A. So let's say the vector I projected was kind of had 3 non-zero entries, x, y, and z. Okay? In the projection, well, that top entry of the projection is going to because this is all ones, it's going to pick up actually all of the non-zero entries. So that top entry is going to be x plus y plus z. So this is picking up too many of the non-zero entries. The second entry is still going to be picking up too many of the non-zero entries. At the bottom there, it's going to be picking up too few. Like it just so happens that one there missed one of the non-zero entries. But somewhere in the middle, this is kind of a Goldilocks lemma, if you like. Everything is just right, and you're picking up exactly one element, one non-zero element of this projection, of this vector in your projection. So again, there's a footnote. I won't make the same mistake as I've just made. I'll talk through the footnote. So you need a little bit of extra tricks to recognize when you indeed only have one thing kind of appearing in one of the entries of the projection. You also need an extra trick to work out, like for our purposes, you don't just need to find a random value amongst x, y, and z. You need to work out which coordinate did, in this case, y come from. Like, it came from the fourth coordinate. That's something you'd need for this graph sketching stuff. So you need some extra tricks for that, but they're not hard to work out. Okay, so that was L0 sampling. I normally just talk about it as a black box, but I didn't want it to be mysterious. So that's the idea behind L0 sampling. So I want to say a little bit about K-connectivity, really because it's a stepping stone to a result I want to get to on spectral sparsification. Okay, because it's going to turn out that not only is it possible for each of you to send me polylog n bits, and for me to work out whether the underlying social network is connected, if you all send me kind of polylog n bits, I'm actually going to be able to approximate the size of every cut, all exponential number of cuts in the entire graph, from just everybody sending me that little bit of information about their local neighborhood. And I think this is somewhat surprising, because we're used to thinking about things like spectral sparsification, like requiring kind of global information about the graph. This is not true at all. Okay, but again, don't want to get ahead of myself. I want to talk a little bit about K-connectivity as a stepping stone towards graph classification. And the result here is that if each of you send me order k polylog n bits about your address book, I'm going to be able to check whether there are at least k edges across every cut in the graph. Okay. So two things I need to show you. I need to show you a basic algorithm we want to emulate in Sketchbase, and I need to show you how to do the sketching. So the basic algorithm is almost as simple as the previous basic algorithm. So here's a basic algorithm for testing K-connectivity. You start off with your big graph, and you rip out a spanning tree, or a spanning forest, F1. Okay, so this is a maximal acyclic subgraph. So you rip out all those edges, we'll call that object F1. Okay, you've now got the residual graph. You now rip out F2 from that graph. You then can rip out another spanning forest. You keep on going for k steps. And so you've ended up constructing k spanning forests, F1, F2, up to Fk. One would hope that you could say, well, if each of those F1 up to Fk was connected, then that was equivalent to the original graph being k-connected. That's not quite true. But what you can say, and again, it's not too hard to prove, and I won't bother going into the proof, is that if you look at the graph you get, just restricting your attention to those trees you've ripped out, F1 up to Fk, this graph is k-connected if and only if the original graph is. Okay. So if we can actually generate F1 through Fk, then we can test the k-connectivity of the original graph. Okay, so let me show you how the sketches work that will allow me to do that. And the sketches actually, to do this, very much build on the connectivity sketch that I had a few slides ago. The idea is, basically, we had a protocol where you'd send me polylog n bits, I'd be able to work out what the graph was connected. It actually allowed me to do slightly more than that. Remember the thing about the red edges? I'd actually be able to find those red edges. So you send me a sketch of your address book, I can find a spanning forest in the graph. I can find F1. The protocol for doing k-connectivity is let's just run that protocol k times in parallel using fresh randomness in each in each copy. So I don't just receive one sketch from you, I actually receive k sketches from you. And I can kind of think about all the sketches of all the individual address books that everyone sent me as just one big sketch of the graph. So M1 being a big sketch of the graph G. I've also got kind of simultaneously, I got enough information to start to sketch another sketch of the graph G, another sketch, all the way up to k sketches. And each of these sketches, M1 of G would allow me to deduce a spanning forest. M2 of G would allow me to construct a spanning forest of G. M3 would allow me to construct a spanning forest of G. So what was the point in doing this k times in parallel? Well, again, this is where linearity helps a lot. Okay, so I'm going to run that algorithm I showed you in the previous slide in sketch space. So I look at M1 of G, and I can find a spanning forest. We'll call that F1. Now, what I want to find is a spanning forest of the residual graph, of the graph that I would have if I first of all ripped out F1. Well, because everything is linear, I can actually do the equivalent operation of ripping out a spanning forest based just on the sketches. So what I do is I have enough information to work out the sketch M2 of G. I've just worked out F1, so I can now just subtract off the sketch of F1. And by linearity, this is the same as having the sketch of the original graph G subtracted, or with F1 ripped out the original graph. And so from properties of F2, I can work out, sorry, properties of M2, I can work out F2. To find F3, well, I just first of all subtract off the sketches of F1 and F2. By linearity, this is just the sketch of this residual graph. That gives me F3. And I can keep on going k times. And I can find my F1 up to Fk, and that gives me enough information to do k connectivity. So again, pretty simple stuff. Just use the kind of the linearity of the sketches to allow me to do this sketching in the projected space, not in the regional space. Okay. Okay, so sparsifiers. The simple result I want to mention right now, although we can do a little bit more, and I'll touch upon that in a second, is what I said earlier, that you can each send me, I guess, a message about your address book of size 1/epsilon² polylog n bits. And from that information, I will be able to estimate every cut in the entire graph up to a factor 1 plus epsilon. And this, the corollary of this will be a dynamic streaming algorithm, and a streaming algorithm that allows me to have inserts and deletes of edges, and allow me to approximate every cut of the graph at any given time using just a factor n times more space than this. Okay, so before we get to, okay, well, I guess on Tuesday, sparsifiers were mentioned a couple of times, but let me just recap. So graph sparsification is all about kind of, well, how do you go about doing some sort of lossy compression of graphs? Okay. When you have some music, some high fidelity music, you can kind of compress it down to an MP3 file. And it's a good compression because most people wouldn't be able to hear the difference. Like, you know, your listening enjoyment wouldn't be impaired that much by using the compressed representation of the data rather than the original data. If you had visual information, again, you could compress it down to JPEG. And for all intents and purposes, it'll be as good as the original. And you wouldn't need to go to Paris. Okay. So there's an equivalent notion, or an analogous notion for graphs, that is introduced by Spielman and Teng, which said that any node on any graph on n nodes, no matter how dense, has a sparse weighted subgraph using only roughly n/epsilon² edges, so that if you look at this sparse weighted subgraph and you measure a size of a cut in that sparse weighted subgraph, it'll be within a factor 1 plus epsilon of the cut in the original graph. So you can take this kind of dense, complicated graph, which could be large in size, throw away many, many of the edges, end up with a sparse graph, and this sparse graph will be for many purposes, if you want to do some sort of graph clustering, if you want to estimate properties of random walks, or, as I said, the kind of size of cuts, then you can use this object as opposed to the original object. So the question I want to address is, well, how do you go about constructing graph sparsifiers in the streaming or this kind of distributed communication complexity setup? And to tell you about that, I first of all need to kind of mention some brief high-level points about it, well, how would you do this graph sparsification in the non-distributed or the non-streaming setup? And actually, it turns out there's a nice simple template algorithm for doing graph sparsification. And that's as follows. You look at the entire graph, and for every edge in that graph, you sample it, every edge UV, you sample that edge UV with probability PUV. And if you don't sample it, okay, you forget about the edge. And if you do sample it, you reweight it by 1 over PUV. And it's not hard to show that by doing this, if you pick any cut in your graph, then the expected weight of that cut after this process would equal the weight originally. Just because with probability PUV, you're weighting it 1 over PUV, and probability 1 minus PUV, you're weighting it 0. Okay. So that's pretty trivial. But what people have shown is that as long as PUV is not too small, you actually preserve nice properties of the graph. So in particular, if PUV is at least 1 over CUV, where CUV is the weight of the size of the minimum cut between U and V. If PUV is bigger than that critical threshold, then concentration of the measure kicks in, and it's not just the case that you preserve the weight of every cut in expectation, but you actually preserve the weight of every cut in the entire graph up to a factor 1 epsilon with high probability. Okay? If PUV is bigger than threshold RUV, where RUV is the effective resistance of the graph, you also preserve all spectral properties of that graph. So the effective resistance is kind of related to kind of commute times in the graph. The basic idea, you take the original graph, you replace every edge with a 1 ohm resistor. And to work out the effective resistance between U and V, this code is going to correspond to the voltage difference, to the potential difference that you get when you inject one unit of flow at U and extract it at V. Okay. And it's not hard to show that the effective resistance, RUV, is always bigger. This threshold is always bigger than that threshold. A recent result shows that the effective resistance of UV is at most a factor n to the 2/3 bigger than 1 over CUV. This relationship is actually being tight. So modulo a factor of n to the 2/3, which is a little annoying. The basic idea is that if you want to construct a spectral sparsifier or a cut sparsifier of a graph, you want to sample edges. You want to sample the edge of the graph with something like a probability t divided by CUV. If t equals 1, you're getting cut sparsification. If t equals n to the 2/3, you're getting spectral sparsification. Okay. So I want to kind of briefly go over, well, how would you go about doing this in the distributed or the streaming setup? Okay. How would you, like, kind of, again, you're all just sending me these address books of your original, sorry, you're sending these sketches of your original address books. I receive these. How can I go about, like, kind of emulating a sampling procedure from these fingerprints and from these sketches? And the idea is as follows. Okay. So goal, we want to sample edge E with probability T divided by CE, where CE was the minimum, the weight of the minimum cut that separated the endpoints of E. So we're going to actually use this idea from the K-connectivity section. If you look at, like, underlying the lemma that I said that, well, if the graph you get by taking the union of F1, F2 up to Fk is K-connected, the original graph is K-connected. is actually kind of a somewhat more powerful statement. That if you take F1 union F2 up to union Fk, for any cut in the original graph that's less than k edges across it, F1 up to Fk will include all those edges. Okay. And I'm actually able to find, remember, I was able to find F1 union F2 union F3 up to union Fk with only a k polylog n bit message from everyone individually. Okay? Okay, so we'll call kind of this union of F1, etc., a k-skeleton. The way we're going to use k-skeletons is as follows. I'm not just going to construct a k-skeleton of the original graph. We're actually going to construct a k-skeleton of a family of log n graphs. So let Gi be the graph that you'd get if you took the original graph and you sampled every edge with probability 1 over 2 to the I. So basically, G0 is your original graph, G1 has about half the edges of the original graph, G2 has about a quarter of the edges of the original graph, G3 is about an eighth of the edges of the original graph, etc. Okay? So you can take your original address books and like kind of imagine what your address book would be like if we kind of subsampled the edges. Because then the corresponding address, subsampling your address book would correspond to these subsampled graphs. Okay? So you then send me the sketch you would send that would allow me to work out the k-skeleton for each Gi, where k is going to be roughly this kind of 2 times t value here. Okay. And the theorem that I'll sketch, although I'll sketch the proof, is that, okay, so I've ended up with getting a k-skeleton from not just G, but G1, G2, G3, etc., etc. And so what you can prove is that the edge E is in one of these k-skeletons with probability at least T divided by CE. Okay? The argument goes as follows. So let C be the edges in the minimum UV cut in G. Okay? If I look at the number of edges in that cut from G1, G2, G3, G4, G5, it's kind of going down every time. Okay? In particular, for a specific value of I, the expected number of edges in the cut, like that's still in Gi, is going to be T. And with high probability, by applying turnoff bounds, you can show that the number of edges across that cut C in Gi is going to be less than 2T. But these skeletons have the property that for all edges that were in a lightweight cut, and where light was size less than 2T, we're going to find all those edges. So this means that the edges in Hi, if and only if their edge was in Gi, and Gi is the graph you get by sampling every edges with 2 to the minus I, so put that into 2 to the minus I, you get exactly that property I was promising. And so that allows you to emulate those sampling algorithms for constructing graph sparse. Okay. I guess I've got a few more minutes. So let me kind of briefly wrap up by, so far in this talk I've focused on graph sketching. And I focused on problems that are related in one way or another to connectivity. So I want to give you a brief overview of other stuff that's been done in the streaming, sketching, and kind of communication kind of models. Mention some extensions of these models, and also mention some kind of open problems that people are thinking about, and that you should think about too. Okay, so there are some immediate applications of these connectivity results. It turns out that kind of after you send me your polylog n bits message, that allow me to work out whether the graph is connected, I could also work out things like, I could estimate the weight of the min spanning tree. I could test whether the graph is two colorable or kind of bipartite. Other algorithms in the data stream setting allow me to maybe kind of estimate the length of paths in the underlying graph. So I can kind of scan through all the edges in the stream. And I can approximate all graph distances up to a factor 2t minus 1, where t is a parameter under your control, using roughly n to the 1 plus 1 over t space. So set t to be log n, being a log n approximation in roughly linear space. But you can make t smaller if you wish. There's a lot of nice work on other basic classic combinatorial problems for graphs. So for example, matching. So you try to find a subset of edges so that no two edges share an endpoint. People have developed algorithms for approximating the maximum weighted matching up to a constant factor. The best constant factor is, as of very recently, is now down to 4, using O tilde n space. Right. O tilde n is just O(n) polylog n. People have also estimated, done algorithms for estimating the number of times a particular small graph appears in your large graph. So for example, estimating the number of triangles in a graph, estimating related parameters like the clustering and transitivity coefficient. People have also come up with nice algorithms for basically emulating short random walks. So for any algorithm you have where one of your primitives is performing these some short random walks as a form of Monte Carlo sampling, there's equivalent ways to do this in the data stream model. I should say, currently, the spanners, the matching, and the random walk algorithms only work in the restricted setting where edges are only inserted in the graph. And they don't work in this case where there's edges, insertions, and deletions. The basic idea being that if you come up with algorithms that are based on these sketches that I've been talking about, they immediately handle insertions and deletions, just because insertions correspond to adding something, deletions correspond to subtracting something. If your whole algorithm is linear, then subtracting something is no more difficult than adding something. Some extensions of the model I'd like to mention. So one of which that has received quite a lot of attention in the database community is the sliding window model. So this is the case where you don't have arbitrary insertions and deletions of edges. You really have implicit deletions. So the idea is you're reading through this long infinite stream, and you want to estimate properties of the last, say, hour or day or month worth of traffic. So basically, all the edges that you received more than a month ago, you want to somehow forget about. But you want to forget about these. Okay, thanks. You want to forget about these edges. The challenge about forgetting about these edges is that you never had enough space to remember the edges you were forgetting. Okay. Yeah, that did sound right. That's what I meant to say. So sliding window, you're in through this big long stream. You're only trying to compute a function of the most recent data. But even the most recent data is maybe too much data to store in your available space on your router somewhere. A lot of the applications where streaming algorithms come into play, you only really have one pass over the data. So if you're doing network monitoring and reading through all these IP packets, you don't get the opportunity to stop the internet and go back a bit and replay a bit. People would be very annoyed if you did that. I haven't tried, but I believe people would be very annoyed. But in other applications, say you have a large data set that resides on a disk rather than main memory, it's perfectly feasible to maybe take multiple passes through the data. And so people have looked at some of these classic graph problems and said, well, how well can you do if you take multiple passes of the data? And there's results like, for example, you can find a 1 plus epsilon approximation to maximum weighted matching if you have roughly 1 or epsilon passes. Another recent piece of work has said, well, there's some problems that you've got no hope of solving if you have these severe restrictions of using small space and only one pass. But suppose there was maybe some third party who is there to make your life easier, who annotates the data. And this could be maybe you've outsourced some of your computation to this third party. And this third party is trying to assist you with the computation you're interested in. So you see the data coming in. This is where your stream algorithm resides. And the idea is you have this third party who's an intermediary between you and the data, who also provides some advice to help you do the processing. But the idea is you don't want to trust this third party, because maybe they'll try to take your money and then return you junk. So they've got to kind of give you a small but useful enough amount of information so you can verify all the answers that are coming from this third party or from this cloud service. There's various open problems in the area. I mentioned that there was something a little bit annoying when n to the 2/3 when it came to spectral sparsification. So one nice problem that I hope will be solved very soon is can we construct a spectral sparsifier in the data stream setting with only order n space. The best argument so far uses n times n to the 2/3 space, which is a bit annoying. Can we construct kind of spanners of sliding window graphs? So spanners are, if you remember, a sparsifier was a sparse weighted subgraph that allows you to approximate eigenvalues and cuts. A spanner is a sparse subgraph that allows you to approximate the shortest hop distance between two nodes. And you can, of course, do what all theoreticians do and try and improve the best known approximation factors for various problems that have been studied. There's actually a large set of open problems in data streams and property testing and communication complexity that you can find at a wiki that was set up that has got a good collection of these problems. Future directions. Almost all the work so far in the community is focused on undirected graphs. And many real-world graphs are directed. So there's a huge opportunity here to get a better understanding of communication and small space stream processing algorithms when dealing with directed graphs. Fortunately, there's some concrete lower bounds you can prove that to work out whether there is a path between nodes U and V in one pass over the stream actually requires you to remember all the edges. But I think there should be ways around this, like maybe either promising that your input graph has certain nice properties, it's kind of generated according to some nice generative model, or maybe you have multiple passes of the graph. Another assumption you can make that would correspond to some practical applications is all the streaming algorithms that people have come up with so far work for A, arbitrary graphs, and B, arbitrary ordering of the stream. So you can be presented this stream in any order. And the algorithms that people design, the goal is to make them correct no matter what the ordering is. Well, in various settings, you could maybe relax this. You could assume that edges are kind of grouped by endpoints, that if it's a weighted graph, the edges come in increasing order of weights. Maybe in some other problems, it's actually easier. You could even promise that the edges came in a random order. A lot of work is focused on when you have O tilde n space. But there are a variety of problems that would be interesting to look at. What happens if you had more space? Could you trade off more space for greater accuracy and faster processing? Or could you get away with a smaller space for specific types of graphs? And there's various deeper connections you could explore with a variety of related areas, dynamic graph, data structures, communication complexity, distributed algorithms. So that's my summary. I talked about graph sketches initially. I then went through some algorithms about how you'd use graph sketches in a somewhat surprising way to get low communication protocols. And then I briefly stated rather than showed that all this connectivity stuff is just one example. There's a whole bunch of problems solved. There's a nice literature that's being built up. Plenty of open problems to be solved. Thank you very much.